All right, hey, let's look at section 7.4 today. This will be day 2. On the previous day, you can remember we worked with those separate differential equations. We worked a little bit on continuously compounding interest, our PERT formula that we like to call it. The amount is equal to the amount present, e to the RT. And today, really, we're going back and working just with growth models and Newton's law of cooling. So, whoops, double click there. The rate at which some particular stuff grows is proportional to how much stuff there is at the time, at the beginning, or the amount present. This indicates that we're working with natural growth and decay models. So, based on that particular statement, the rate is my dy dt. The amount of stuff, the rate at which that stuff is decreasing will be equal to some proportionality constant, right? Proportionality constant, and then the amount present at the start of it. So the amount present generates that differential equation for us. So that particular statement is always an indicator that we're looking at natural growth and decay. If we solved it like we did in day 1, you come up with this solution equation. And it's y equals y naught, the amount present, e to the kt. The law of natural growth, if stuff is increasing, we're going to be seeing a k that is positive. If we have a decreasing or decaying model, it will be less than 0. K will be less than 0. The rate at which stuff grows is proportional to the amount of stuff there is in the beginning. What am I looking at here? Well, it tells us that it's just obeying the laws of natural growth. And we start, let's do this problem. We start with 10 pounds of stuff. What kind of stuff? I don't know. Maybe population, maybe bacteria, anything that undergoes an increase here. 4 hours later, we have 15 pounds of stuff. When will we have 20 pounds of stuff? Just a very common growth problem. So if I go back to the sentence, I can stop and rewrite based on what I was given there. So let's just quickly rewrite this sentence here. We start with 10 pounds of stuff and 4 hours later we have. So I'm thinking of the y naught, e to the kt model. And it said we start with 10 pounds of stuff. So 10 would be my y naught. 4 hours later, that's my time. E to the K4. And then we have 15 pounds stuff. 4 hours later, we have 15, my ending amount. I end with 15 pounds. And I can write that equation. I think you guys probably can solve that. We would divide by 10. That's going to give us 3/2 equals e to the 4k. Natural log both sides. I'm going to call this natural log of 1.5 just for ease of writing it. Equals 4k. Come in with my k quantity, my proportionality constant, 1/4 natural log 1.5. So the first task was really to come up with what is the proportionality constant. And if they give me a beginning amount and an ending amount, and amount of time that it took, I should be able to get that. Next, what do we want to do here? Oh, how long does it take to get 20 pounds? How long until y equals 20 pounds of stuff? Well, I come back to this basic equation of the growth model, and I say I want to finish with 20 if I started with 10 e to the k. I know my k. It's 1/4 natural log 1.5. And then the question is, how much time is that going to take? So time is really the variable we're trying to solve for on this one. And I'm sure that you can process through on this. Let's divide by 10. 20 divided by 10 does not give us a half. It gives us 2. e to the 1/4 natural log 1.5 times time. Natural log both sides. That e will wipe away and we'll get 1/4 natural log 1.5 times t. Divide by the quarter natural log. So actually I'm going to multiply by 4 first, clear that 1/4. That's gone, and then I'm going to be able to, so I've got this, oh, sorry about that. I've got that gone because I brought it over as a 4, didn't I? So I divide by 1.5 now. Natural log 1.5 though, and that should give us our time element. And according to my previous work, either it's 2.838 hours from 15, but I started with 10. So from the beginning of time here, my amount is going to be 4 hours plus the 2, so I'm going to end up with 6.838. Because legitimately, there's nothing stopping you from saying, you know what, I'm going to start with 15 and move forward, right? It's just all a matter of what time element we want to start from. And I'm just going to say from the beginning part, it'll take 6 hours to get to 20. Example 2, the secret organism Q doubles in size every 6 hours. How long does it take to get 100 times as big? The secret organism doubles in the size every 6 hours. So let's follow the law of natural growth and decay. So y equals y naught e to the kt. Once again, we want to try and find k first. Sorry about the disappearing ink. So the secret organism doubles every 6 hours. So what was my beginning amount and what was my ending amount? Good question, huh? Well, it says it doubles, so I could generate any numbers that make it double. I could say I started with 1 and I finished with 2. I could say I started with 10 and I finished with 20. I could even say I started with 75 units and I finished with 150, right? Your choice. I think the two easiest numbers to use are 1 and 2, so that's what I'm going to choose to use. I started with 1 and it doubles, so I finish with 2. E to the k times 6 hours, so the time it took for this to happen was 6 hours. And we want to find k, don't we? Because we don't have k. All right, I should have said, okay, let's find k. 2 equals, let's go e to the 6k. We know we should natural log, so natural log 2. Oh, it's like it's doubling, right? Equals 6k, divide by 6, and we're talking about 1/6 of natural log 2k. That's a starter part for us. Now we know our k, and I got to go back and reread my question. How long does it take to get 100 times as big? Well, I'm going to say my initial amount then is 1, and I want to get 100 times as big, so my ending amount is going to be 100. And the question is, how much time does it take? And we know our k this time, it's 1/6 natural log of 2. So, setting this up, I finish with 100 when I start with 1. E to the 1/6 natural log 2 times time. If we want to solve this, we'll have natural log of 100 equals 1/6 natural log 2 times time. The e went away when I natural logged. And then I'm going to multiply by 6 to get rid of the 1/6. And then I'll divide by that 2. So I get t equals 6 natural log 100 divided by natural log 2. And if you calculate that out, I'm going to steal this answer. I believe the answer turns out to be 39.863 hours. Hopefully this is really just a lot of review for you. Example 3, radioactive decay. The half-life of radium-226 is 1,590 years. A sample of radium-226 has a mass of 100 milligrams. Find the mass after 1,000 years. What does half-life mean? Will I be beyond half of this original 100 milligrams if I wait for 1,000 years to pass? Well, the answer is no. I won't even be halfway yet because this told me the half-life was 1,590 years. So what does half-life mean? It gets you to the amount of time it takes to get to half the original amount. The amount of time required to for a substance, how about? For a substance to decrease to half the original quantity. That's a Q there, quantity. That's what it means to have half-life. This half-life question, well, let's see, what do I have? I have a time frame of 1,590 years, and it says it takes it that amount of time to go down to half the original quantity. What was my original quantity? Good question. They didn't tell us, did they? Well, let's just create it then. I guess you could go with the 100, but I'm just going to create. I started out with 1 unit, and I'm going to finish then with a half a unit, right? I don't know what my proportionality constant is for radium-226. There's probably a table somewhere where you could get that, but we're going to just go ahead and solve it on our own. So using this information, we can go into our y equals y naught e to the kt format and find our k. So I'm going to finish with half the original quantity that I started with, which was 1. I would have e to the k, and time frame was 1,590 years. Natural log both sides, and we're looking at the natural log of 1/2 equals 1,590 times k. So k is natural log of our quantity 1/2 divided by 1,590. So there is your k value. Now we got to find the mass after 1,000 years. So that's going to be a little bit more work. I guess I can get rid of this. And after 1,000 years, so our time element is 1,000. We started with our y naught is going to be that 100 milligrams, and they want to know what's the ending amount. We do have our k value that we had just solved, so k of 1/2 equals 1,590. Let's pop it into an equation here. So, y, our finishing amount, equals 100, the starting amount, e to the natural log of 1/2 over 1,590, and 1,000 years. Solving, oh, that's just going to be straight into the calculator. Looks like I came out with 65 milligrams. So the amount equals 65 milligrams. A nice one to solve. When will the mass be down to 30 milligrams? Well, let's talk about our starting amount being 100 milligrams. Our ending amount then would be 30 milligrams. Time is what we're trying to find, and we still are having that same k value because we're still working with that radium-226. All right, so we've got our critical pieces, and we just put them into our equation. Y equals y naught e to the k t. Finishing with 30 when I started with 100. E to the k, natural log 1/2 1,590 times time, and then just solve for time. So the first thing we're going to do is divide by 100. So that's going to be like 3/10, because the 0 would delete there, wouldn't it? Which really comes down to 0.3. equals e to the natural log 1/2 1590t. Natural log both sides, ln 0.3 equals ln of 1/2 divided by 1590 times time. And we'll divide by this. So time would equal natural log 0.3 divided by natural log of 0.5 if you want, or 1/2, divided by 1590. That becomes then a multiplier times that. And that time element is 2761.775 years. A bit of time, huh? Around 2,000 years. All right. Finally, into Newton's law of cooling. Newton's law of cooling states that the rate of change of the temperature of an object is proportional to the difference between its own temperature and the ambient temperature, the temperature of its surrounding. And then we get into this meatball problem. So this statement that we just read correlates to this differential equation. The rate of change of temperature, the rate of change of capital T. So capital T in my case here is going to stand for the temperature. The rate of change of temperature of an object. So let's even put of object, because we'll get a couple different temperatures going. All right, Newton's law of cooling states the rate of change of temperature of an object is proportional to the difference between its own temperature and the ambient temperature. So the temperature of the surrounding is this T sub S, temperature of surrounding medium, or the air, or whatever that happened to be. If it was packed in ice, the temperature of the ice. This is also referred to as ambient, isn't it? The ambient temperature. T naught is my initial temperature. Let's get all our variables accounted for here before we start off. If I solve this differential equation, which takes a little bit of time, I end up with a statement like this, which I can convert to this. So where does that take us? Well, it's just kind of helpful to remember that T minus Ts equals T naught minus T sub S, the object, the initial temperature minus the surrounding temperature, e to the negative kT. Negative because it's called Newton's law of cooling. So you could use negative K. I tend to just use K. If it turns out to be cooling, it's going to be a negative K. If it turns out to be increasing because the surrounding temperature is warmer, then it's going to be a positive K. So I would almost just take that off, you guys. Let's just talk e to the KT. Another change I would make would be this temperature. I'm even going to say final. Is going to be, I'm going to add T sub S over to the other side. And then I think it starts looking a lot like an equation that you may have used in pre-calc. I believe that's the one they give you in pre-calc. It's also somewhat easy to remember because if you think of SOS, like help, I don't know. SOS is the order in which those subscripts come. So very seldom has this been an AP question, but still it could, and it's good to know. You could even, like forensics, use the body temperature that they found it at to estimate how long the person had been, had passed, how long ago it passed away, because Newton's law of cooling works for our bodies as well. Kind of gruesome, huh? Let's go through this one. Part A. A 250-degree meatball is removed from a simmering pan and set to cool on a plate in a 70-degree room. In 3 minutes, it is 200 degrees Fahrenheit, so it's gone from 250 down to 200. How long before it falls below the 140-degree range into the danger zone where bacteria can thrive? So let's just kind of note what information we have. The meatball, the initial temperature of our meatball, T naught, is 250 degrees. The surrounding temperature was what? Will it be the room? 70-degree rooms, so 70 degrees. And we want to know when it will reach its final temperature of 200 degrees Fahrenheit. Oh, hold it. We want to get down, well, you know what, let's talk about the 200 first, and then finally we're going to ask how long to get down to 140 degrees. But this particular set of information, the T, 0, S, and F, will help us find our K value when we knew that it took a certain amount of time. It took 3 minutes for it to decrease from the 250 to the 200. So this is going to be critical to finding K value. And then we can finally go into the 140-degree question. All right? So let's get the ball rolling here. Really, it's just plug and play, isn't it? I'm going to use this equation up here. So my temperature final, the meatball came down to 200. I'm sorry. The meatball came down to 200 degrees. It started at 250 plus, oh, that's a lie, isn't it? TS is 70 degrees. And here's where the temperature of the object comes into play, 250 minus the temperature of the surrounding, which is 70 degrees. E to the K, don't know the K, times 3. So what can you take from this? The larger this temperature differential is, the faster the cooling occurs, right? So initially, when things are cooling and we start at a high temp, it cools quickly and then it starts slowing down, right? Yeah. Initially, we're going to have a large temperature differential so that this part changes actually quite quickly. And then as these two numbers, can you see which ones I'm pointing at, you guys? Should I point some more? These two numbers, once they start closing in on each other, then the temperature starts slowing down. The temperature change starts slowing down. Alrighty, so let's work from here. We got 200 equals 70 plus. Difference between 250 and 70 is 180. E to the 3K. Now it's just equation solving. And I know you can handle that. Let's subtract 70. That gives us a 130 equals a 180. E to the 3K. Divide by the 180. So I'd have 130 over a 180. Let's cancel those zeros. Equals a 3K. So the zeros are gone. So we're looking at 13/18 equals e to the 3K. Getting to K. Hey, we are getting to K eventually, right? Natural log 13/18 equals the 3K. Divide by 3 or multiply by 1/3. I'm going to do the 1/3 business. Finally, we got our K. Perfect. Next, what was the final question? I got to go back up and reread, as we often do in word problems. How long before it falls below 140 degrees? So now I have kind of the startup of a mini new question. I want to know temperature final equals 140. How long does it take? My surrounding temperature still is a 70-degree room. And I am going to start from the premise that my object was just taken out of the oven at 250 degrees. And I'll talk about how long it takes it to go from 250 all the way down to 140. You have to read those questions carefully because sometimes they ask, how much longer will it be? And then I would have worked off the 200 degrees that it was already positioned at. All right, into our temperature final equals SOS, right? Temperature of the surrounding plus the temperature differential between the object and the surrounding, e to the KT. See how that SOS can come in handy, you guys? All right, so temperature of the surrounding is 70. Temperature of the object, we said we're starting immediately from pulling it from the oven, 250. Temperature surrounding is 70. E to the K is 1/3 natural log 13/18. And T, oh, I think T needs its own color. T is what we're trying to solve. Do you want me to solve this? Well, this is getting lengthy. Wow. 140 equals 70 plus 180 e to the 1/3 natural log 13/18 t. Subtracting a 70 gets me a 70. Equals 180. I would divide by 180 also, wouldn't I? Just to save a step. E to the 1/3 natural log 13/18 time. Got to get the exponent variable of t down, so natural log. Natural log, can I call this 7/18? You bet I can. Equals t, and then I'd have this stuff, so I'm going to divide by natural log 13/18. Dividing by 1/3 is like multiplying by a 3, and there's your time frame. And I do have an answer for you, I promise, if I can find it. Maybe I lied, guys. I've got it sitting at this state right here too. I never did solve it. You'll have to use your calculator. All right. Thanks for being so patient. I think we can skip number 72. And you have a little My Math Lab to do. Just lots of growth, decay, Newton's law of cooling. 6 of them, 7 of them, 7 of them, I guess. Have a great day. Bye-bye.